All right, I'm gonna go over this pretty quickly. Basically, alkanes. What do we use alkanes for? This is what fossil fuels are. Okay, anything from 1 carbon to 20 to 30 carbons. All right, our pretty much our existence in our life is all dependent on fossil fuels. I mean, natural gas, our cars, our clothing, everything somehow came from a fossil fuel of some sort. Okay, so natural gas is basically methane. I believe it's also ethane. They don't put that here. They really imply just methane, but natural gas is also composed of ethane. Um, Petroleum is a mixture of refined um, fossil fuels where they boil it off and they extract out different size molecules all based off the boiling points. All right, methane, ethane, propane, and butane is a gas at room temperature. All right, pentane is the first one that's a liquid, and it's a pretty volatile liquid. Hexanes is a liquid. Heptane, octane. You all know what octane looks like and smells like. All right, it's basically our gasoline. That's octane. Nonane. All right. Once you get to like 20 to 30 to 40 carbons, now we get almost into solids. Those are is like a wax. Our candles. All right, or tar. Tar is kind of a perfect example. Tar is kind of a combination of a lot of different um, alkanes, mostly at the higher ends. I think in the teens into 20s. Okay, so gasoline and kerosene and diesel fuel is a really thick fuel. That's more the higher end, the 15 like to 18. Plastics, drugs, fabrics, dyes, and pesticides kind of come from. Well, it's not a fossil fuel, but you can take one of these alkanes and do a chemical reaction on it and turn it into a pesticide or plastics or drugs or things like that. This is kind of to show you the refining process. Like if you just drive down Highway 25 these days and you see all the fracking um, areas, you can kind of see smaller versions of these. All right, and basically what they are is all of the fossil fuels are going up. So this is kind of a cut view of this. Okay, and basically all depending on the boiling point. So it comes in from the ground. The very high boiling point molecules all come out of the top of the, as a gas. Sometimes you actually see it burning at the top. Don't you notice a flame that's burning at the top? Sometimes they don't care about natural gas. They don't want to collect the natural gas. So they just burn all the volatile stuff. So all the boiling points, things that boil below like 20 degrees Celsius, methane, ethane, propane, and butane. And then they fraction off the gasoline, which comes off a little bit high, a little bit lower, and then so forth and so on. Okay, so asphalt is the real thick tar, real heavy molecules. As soon as it comes through here, it just kind of falls down and it goes out. All right, so that's kind of what they are showing you here. All right, physical properties. We kind of know physical properties. Nonpolar, carbon-carbon, CH bonds are nonpolar. Weak intermolecular forces. In fact, what type are they? Do you remember the names? London dispersion or van der Waal. Just depends on what you like or learned. Or van der Waal. Van der Waal. Smaller alkanes are gases at room temperature. Okay, larger ones are liquids. There are also ones that are solids. Alkanes are insoluble in water. Okay, they are less dense, so they float. So if you have, if you remember lab, you had water on the bottom, and I think we use pentane. Is that correct? Pentane floated on top. Okay, also an oil spill. Think of a tanker that gets a big hole in it and the oil spills out. Where does it usually end up? It's floating on top of the water. You can see an oil slick. That's why it's called an oil slick. All right, just to kind of give you some boiling points of things. All right, like I said, everything from 1 to 4 boils less than 0. Pentane is the first liquid. All right, then hexane. As you increase the surface area, increase the boiling point. That makes sense because we now have more van der Waal forces. So I got van der Waal forces in 6 carbons opposed to only van der Waal forces with only 4 carbons. So more intermolecular forces. Okay, increased surface area, which in turn increases intermolecular force. You have more intermolecular forces. All right, alkanes don't have a functional group. Basically, the two main types, or I'm sorry, type of a reaction is a combustion reaction, which you've learned in Gen Chem. You take some sort of hydrocarbon, CXHY, plus oxygen, always gives you CO2 and water. That's like our gasoline. That's basically what hydrocarbons do. That's the most common thing that they do. Okay? It doesn't matter what the hydrocarbon is. If it's one carbon or a trillion carbons, they all do the same thing. Combustion. Here's a perfect combustion. Here is methane. All right, methane, natural gas. You add oxygen, a flame, get CO2 and H2O. Isooctane is a high octane component of gasoline. All right, so this has 8 carbons, burn it in oxygen, get CO2, water, and energy, and that's what moves your engine. Now, if you don't have enough oxygen, you get an incomplete oxidation, and that's when you start forming carbon monoxide. All right, so carbon monoxide is formed here, but that's when you do not have a stoichiometric amount of oxygen. Remember that word, stoichiometric amount? That means I don't have a 2 to 3 ratio. I'll have like a 2 to 1 ratio. All right, if I don't have enough oxygen, then they will not get a complete reaction. We know carbon monoxide is a poisonous gas. Yeah, but I don't know if you guys realize this, but carbon monoxide has a similar structure of oxygen. Carbon monoxide looks like this. Oxygen looks like this. Oxygen bonds to our iron in our hemoglobin. All right, our blood has iron in it, and what happens is when you breathe in, the oxygen gets bound to the iron in our hemoglobin, and then the blood goes through the body, releases the oxygen into the muscle, and then your muscle now has oxygen. Then the blood comes back to your lungs, gets oxygen, and does the whole process over again. Well, carbon monoxide is very similar in size as oxygen. All right, so if you breathe it in, it goes into your lungs, and it actually, the carbon has a negative charge on it. And because of it, it binds so tightly onto iron. Verse FeO. Okay, in this case, the iron and the oxygen, this bond can break easily. Iron can pop, or oxygen can pop on and off. In this case, this bond is so strong that it doesn't want to come off of iron. Okay, so what happens? Carbon monoxide goes in your lungs, it goes onto iron, your iron goes to the body, tries to release the CO, but it doesn't. So what happens? The muscle no longer gets oxygen, or your brain, specifically your brain. Your brain gets no oxygen because nothing is releasing off of the iron. So because that bond is so strong. So that's basically how you die, is because, well, first you probably go brain dead, and then eventually all the muscles eventually die because you don't have any oxygen anymore and you're not breathing. So that's how carbon monoxide poisoning occurs. CO is very similar to the size of oxygen, except it's bonded so much stronger to iron. So in order to cure yourself of carbon monoxide poisoning, you actually have to have an oxygen mask. Okay, our oxygen in our air is about 20% oxygen. Now, if you swamp your body with oxygen, if you put like a trillion-fold excess of oxygen first versus your CO, then this iron is bombarded with O2 molecules, and since it's hitting it so often, eventually that CO will all pop off and go away, and that's kind of how you can reverse carbon monoxide poisoning. But you have to know that you have been poisoned by carbon monoxide. You have to still be alive, and then you have to go to the hospital and get oxygen tank. But if you are just if your body is just swamped with like CO, there is pretty much really, you don't have a hope. You will probably pass out in about 1 to 2 minutes, and that pretty much be it. So that's why we have CO detectors in our house, because you can't smell it, you can't taste it, nothing. All right, let's talk about things a little bit more upbeat. Another reaction is halogenation reaction of alkanes. What you can do, so alkanes don't have a function, but you can attach halogens to them. All right, X is usually the universal symbol for halogens, and in this case, X2 means bromine or iodine or chlorine. You could also do fluorine. Fluorine's not as reactive, but you could do fluorine. Okay, and basically it's the alkane plus this is Br2, plus your halogen in the presence of light and heat, you can actually take off the hydrogen and put a halogen in place of it. All right, it goes through a radical reaction, and it's kind of how we make halogenated compounds. All right, so halogenation is a substitution reaction where you substitute a hydrogen for an X. All right. You can make alkyl halides. This is how you make the functional group of alkyl halides. All right. So this is it. That's the end of chapter 12. We learned everything we know about alkanes. Not really a lot of information, but I'm sorry, it is a lot of information, but believe it or not, it's not very exciting. There's lots of other functional groups that there's a lot more exciting stuff that we'll learn. But this is the start of organic. This is kind of where we start. And if you have any questions, obviously email me, come to office hours, or we will talk about it in class.